I want to do just a quick summary of the different types of stereoisomers that we had in this chapter. First, let's just do our number of chiral centers. So if we have 0 chiral centers, remember it is going to be achiral, right? So it's not optically active, right? Chiral means optically active. Achiral means it's not chiral, so it's not optically active. Optically active means it's going to rotate plane polarized light. So if I don't have any chiral centers, it's not going to be chiral. If I have 1 chiral center, it is going to be chiral. So it is optically active. And then if we have 2 or more chiral centers, it could be chiral or it could be achiral. And what we're doing is we're looking for that plane of symmetry, right? It could be meso. If it's meso, it has a plane of symmetry and it's achiral. So 2 or more chiral centers, chiral or achiral, look for that plane of symmetry, right? If something is achiral, it will have a plane of symmetry. The types that we saw in this chapter of stereoisomers, we had enantiomers. So these were our non-superimposable mirror images right? If we were going to assign R and S configuration, they're going to have opposite configuration at all chiral centers. If you had 4 chiral centers and say the first one was R and then S and then R, then its enantiomer will be S, S, R, S, right? Every chiral center is going to be the opposite. So mirror images of each other. If we try to line up those mirror images, we can't, so non-superimposable. And then my configuration at all my chiral centers are going to be the opposite. I just have to have at least 1 chiral center. So I could have 1 or 2 or 3. It doesn't really matter as long as I don't have 0, right? 0 isn't an option, but I could have 1, I could have 12. So non-superimposable mirror images, opposite configuration at all chiral centers. And then from a physical property standpoint, they had the same physical properties. Except that they rotate plane polarized light, so light that's all lined up in one direction. You should say in one plane, right? It's actually going in 2 directions. In opposite directions. I do have a new term here, and that's a racemic mixture. So if something is racemic or exists as a racemic mixture, you don't actually need the word mixture. What that is it's a mixture that contains 50% of the D enantiomer, 50% of the L enantiomer. And overall, that mixture is not optically active because those 2 rotations cancel each other out. So if you have a sample of molecules and half of those molecules are going to rotate light to the left and the other half are going to rotate light to the right, the net effect is that your light is not rotated. So this is a 50-50 mixture of enantiomers. Essentially, it's not optically active as a mixture. Because the 2 enantiomers, we should say the rotation of the 2 enantiomers, cancel each other out. So essentially our net effect is that we have no light rotation. If it wasn't an equal mix, right, if you had more of one than the other, then the net effect is to still rotate light. But if you have an equal amount of the two enantiomers, the left rotation and the right rotations are going to cancel, and our net effect is that it doesn't rotate light. So this is not optically active. So do know this one. I meant to just underline it again. Do know this term. It is going to come up again. So enantiomers. Diastereomers were our other type. And our diastereomers are stereoisomers, but they're not mirror images. They are stereoisomers though, so they're not identical. Be careful for that. So stereoisomers that are not mirror images, right? They're not identical. And they have opposite configuration at least one carbon, or at least one chiral center, sorry. But not all chiral centers. Right? If it was all, they would be enantiomers. If it was the same at all, they would just be the same. So opposite configuration at least one chiral center, but not all chiral centers. We do need to have at least two chiral centers. Right? There's no way to achieve that sentence right above it if I don't have at least two, right? I can't be the same at one chiral center and opposite at another chiral center if I only have one chiral center. So I need to have at least two chiral centers to have a pair of diastereomers. So kind of a real typical question I ask is I'll give you sets of molecules and I'll ask you, are they enantiomers? Are they diastereomers? Are they meso? Are they none of those things? Are they just plain identical? And if they only have one chiral center, diastereomers are not a choice. Just eliminate it from your choice. Now you only have enantiomers, and they're the same thing. They're identical. So diastereomers, we need at least two chiral centers. And then these actually have different physical properties. And then we also had meso compounds. And our meso compounds are going to be achiral molecules that have chiral centers. So achiral molecule that have chiral centers. Because they're achiral, they're going to have that plane of symmetry. Remember, anytime something's achiral, it has a plane of symmetry. So you can draw a line somewhere through the molecule itself where it reflects back at itself. So has a plane of symmetry. I could give you two, kind of like we did in the last video where we had an example where I had opposite configuration and it looked like it was an enantiomer, but remember they are superimposable. So if we go back up to this one, right, enantiomers, opposite configuration, all chiral centers, but also they are not they're also not superimposable. So opposite configuration, all chiral centers, and are not superimposable. These ones, it could be opposite configuration, but they are superimposable. They do have that plane of symmetry. So be careful not to get your meso compounds goofed up with enantiomers if you're just looking at configuration. You can't always just look at configuration to figure it out. And then be careful not to get meso compounds confused with something that's just not chiral, right? Something that doesn't have a chiral center. So meso compounds have to have a chiral center, right? If I was to look at something like this, and I'm going to put a bromine versus this one, and I'm going to put 2 bromines. Now they both have a plane of symmetry. The first one I would actually, there's a hydrogen on here too, and I would actually cut right through the bromine and the hydrogen. The hydrogen's going back. This has a plane of symmetry, and I would cut right through here. So they're both achiral. But this one is meso. This one is not meso. Right? The difference between them is that these are chiral centers. This one has no chiral center. And it doesn't always have to be a ring, but it's kind of the easy way to show it, right? There's a hydrogen, there's a bromine, so that's 2 things. But then when I go in this direction, it's the same as when I go in this direction. So I don't actually have a chiral center on that molecule. Ooh, wrong color, green. It looked like a solid line, so it looked like I had stuck a methyl group on there, so I wanted to make sure it was dotted. So 2 molecules that are achiral for different reasons, right? One just doesn't have a chiral center. The other has chiral centers, but it has that plane of symmetry, right? So be careful not to get those 2 mixed up. So meso, not meso. Both of them achiral. So achiral molecules that have chiral centers.